equals mc squared is one of the most confusingly explained concepts ever. Not to say that other physics equations are explained well, because physicists generally aren't very good at explaining concepts. But I remember I was always quite frustrated by this growing up. It's just because of the prominence of this equation. Everyone's heard of E equals mc squared, right? So I would hear it again and again, and I never understood what it meant. And every explanation that I heard was either way too high level or way too low level and dumbing things down. And the low level explanations involved a lot of hand waving, like, oh, something something nuclear fission, something something nuclear weapons, boom, explosion, scientists, Einstein equals mc squared. That's the explanation that you get. That's saying, oh, this is mass, this is energy, this is the speed of light. Okay, fine. But that really doesn't help me understand it a lot, because there are a number of things that are a bit confusing. For example, I understand in nuclear reactions you can get a lot of energy, but isn't that kind of like saying, running shoes plus athleticism equals sweat? Like, I understand that is sort of true. Like, if I have running shoes and I display athleticism, then it produces sweat. But then why is there an equal sign there? Shouldn't it be something other than an equal sign? Shouldn't it be like running shoes plus athleticism, it begets sweat? Or like an arrow or something? Like a cause and effect? Or like what is happening? What is the equation actually expressing? Because you're not saying that those things are literally equal, right? Like shoes, that's an object. Athleticism is like an activity, and sweat is, I guess, also a material, an object. So, the analogy kind of breaks down, but let me give you a multiple choice quiz, okay? What does E equals mc squared say? Option A is that it's saying that you can convert energy into mass and vice versa, and when you convert energy into mass and vice versa, it tells you how much energy you're going to get relative to how much mass you put in, or how much mass you're going to get relative to how much energy you put in. Okay? That's option A. Option B is you're saying that energy literally is the same thing as mass, but that's true in like a weird semantic way that isn't really useful, or doesn't make a lot of sense. Option C is it's saying that energy like contains mass, so bound within mass is also energy, or something like the opposite. And if you look closely enough in energy, you find mass. So we say they're equal, but it's like one is inside the other. Is it like that? Or option D is it's a weird combination of some of the other items in this list. Okay, the answer is sort of D, but it's mostly B. I mean, I think it'll make more sense as I actually explain it, okay? So I am going to explain E equals mc squared, and I'm going to do it in hopefully a way that actually makes sense, and the first time that you're ever going to hear an explanation that makes sense, but I'm probably going to say some things that are wrong. I'm probably going to make some mistakes, but we'll edit that out. Okay. First of all, I guess I'll start here. It is literally true that you can convert mass into energy, and you can convert energy into mass. Not you, but like, it's a thing that can happen. And when you convert energy into mass, or when you convert mass into energy, then E equals mc squared is saying how much energy you're going to get, basically. How much you're going to get. And what is the equation saying? It's saying E stands for energy, M stands for mass, C, that's just a number. C is just a number, okay? But it's a number in terms of speed. So it's like a speed-related number. And squared is just saying we're squaring that. So we're multiplying it by itself. So it's like we're taking a number in terms of speed and we're multiplying it by itself, okay? That's what that is. But that's just a way of saying, here's how much of this number you're going to get. Okay, fine. But another thing that was confusing to me is, like, isn't this just a unit conversion? Like, isn't it kind of arbitrary how we measure these things? Like, what if we were to measure mass in such a way to where you automatically do the multiplication by the speed of light squared. I think I'm getting ahead of myself, okay? We'll leave that in a second. But yes, it's literally true that you can convert one into the other, or vice versa, and that's saying how much you're going to get. So like, because speed of light is a large number, if you convert a tiny bit of mass into energy, then you're going to get a lot of energy. Because, just to put it in perspective, right? Speed of light, that's really fast. And speed of light squared, that's even faster. So however much mass there is, the speed of light, if that's how much energy you're going to get, then that's a lot of energy. And it makes sense that it would be measured in terms of speed, because like, that's something you can do with energy. Think of like kinetic energy, right? Kinetic energy is saying it's in terms of speed anyway. So it's fine to do that conversion in terms of speed, because energy already has the concept of speed. So that's what that is. Now here are a few problems. Problem number one. This is an objection you might have in your head. I don't know if you're actually thinking this, but you should. The first objection is, doesn't this violate the law of conservation of mass? Because I remember when I was in school, I was in middle school, whatever, I was learning some things about physics, and they taught me mass cannot be created or destroyed. That's the law of conservation of mass. So how can it be that through the nuclear operations, those are the operations that convert mass into energy. They're rare, but they can happen. Through nuclear operations, you can convert these things. But how is that possible? If you can just convert mass into energy, then aren't you losing mass? But then the law of conservation of mass is not true anymore. So how does that give, right? So here is the answer. The answer is that the law of conservation of mass is wrong. That's right, you were just taught a thing in school, it's false. There's a way of saving it, but the way of saving it is to say that we're just going to make an exception for nuclear. So we're just going to say, oh, it's true within the classical context. It's true within like Newtonian physics. But then we learned about Einstein, and now it's not true anymore, because we know about these things where actually you can lose mass. So that's kind of an unsatisfying answer. You're just explicitly creating a carve-out for certain operations that violate this principle, which is kind of like no true Scotsman. Like, you're saying, okay, except for these things, it's true. That's one way. The second way to save it is even less satisfying. The second way is to say the law of conservation of mass is true, but it's not the law of conservation of mass, it's the law of conservation of mass energy. So if you track the total amount of mass energy, then it always stays the same, because you're converting mass into energy, blah, blah, blah. That's true, but it's even less satisfying, because now it's not the same law anymore. It's like, we're getting into the law of conservation of energy, which I think is a far better expression of this, but we're going to get to that. We're going to get to the law of conservation of energy in a second. But first, let's keep going with this. That's the first objection out of the way. The second objection is, okay, fine, like, the law of conservation of mass is false, but surely you're not telling me that elementary particles can get created or destroyed, because I know that that's the case, right? And I vaguely remember in middle school or whatever, when I was learning about physics, I also learned there are these things called protons, neutrons, and electrons. And it's impossible to create or destroy protons, neutrons, and electrons. And maybe you have a nuclear operations, fine. But in the nuclear reactions, you're not creating elementary particles. The elementary particles already existed. You're just splitting the atom, or you're putting the atom together, you know? In fusion, you're putting the atom together. In fission, you're splitting the atom. These work, but that's not creating fundamental particles. So how can you tell me that mass can be destroyed if, like, I know about this other law that says fundamental particles can't be created or destroyed? So that's true. That's called the conservation of the I always pronounce this wrong. Baryon number. That is true. The conservation of the Baryon number is true. However, here's why it works. It works because the amount of mass that something has is not determined by just counting up the number of protons, neutrons, and electrons that you have. The same protons, neutrons, and electrons have different masses based on their configuration of what atoms they're in. So, like for example, for helium-4 versus separate nucleons, let's say like helium-4, it's made up of 2 protons and 2 neutrons. But if you calculate the mass of 2 free protons and two free neutrons, then the mass of the 2 free protons and the 2 free neutrons is greater than the mass of what those neutrons and electrons would be if they were bound up in helium-4. So the same fundamental particles, depending on whether they're free or whether they're bound up, will have different masses, and that's why nuclear reactions can create mass, because you're just changing the configuration of the protons, neutrons, and electrons, and that's changing the mass of the items. So like, this was kind of a mindfuck when I learned this. The thing is, like, you think of mass as being fundamental, and I think Wikipedia lists it as like, it's a fundamental property. Let's look it up. Define mass, Wikipedia. It says, mass is an intrinsic property of a body. If you go to the periodic table and you look at each of the elements, at the bottom of the cards for each of the elements, you'll see a number. Like, it says, for hydrogen, it says 1.0008. So that is the atomic weight. That's saying how much mass there is. And it's just, we have invented this thing called the periodic table, which tells us for each of the atoms how much mass it has. And that's just how we say how much mass it is. There's nothing other than that. Now let's get into what even is mass. So I'm talking about mass. What is this concept of mass? So mass is a property in physics that does two things, basically. The first thing that it does is it determines your momentum. So, like, if I have a cart and I have a cart going down a track, then it determines your acceleration. So momentum, acceleration, same thing. So it determines how difficult it is to accelerate you. So an object with more momentum, with more mass, is going to be more difficult to accelerate than an object with less mass. So if I have a big cart going down the road, then if I have a small cart that pushes me, it's going to cause less acceleration than if I'm being pushed by a big cart. So that is true because the small cart has less mass and the big cart has more mass. So that's saying that the amount of mass that these carts have will have an impact on how much acceleration I'm gonna have. And also how much mass my cart has tells me how much it responds to the acceleration that's being caused by the forces put on me by these other carts. So it's saying my mass relative to the mass of other objects, that's saying relatively how much those other objects can impact my acceleration. Okay, that's the first thing that mass does. The second thing that mass does, which is not the same, is it determines like how much gravity you have. So an object with more mass, it's going to have more gravitational pull. It's going to pull objects towards it more. And also it's going to be more pulled towards something. Like if I'm heavier, I'm going to be pulled towards the ground more in a way, using like in layman's terms, right? And a large body, a large planet has a more massive planet has more gravitational pull. I don't think people respect the degree to which the fact that those two things are the same is unintuitive. It's not completely obvious. It's not something that you would assume, or it's obvious to us because we live in this world where this is the case, so we don't know it any other way. It's like we deal with these forces every day in our everyday lives. So yes, obviously we know that a heavier person will, is more massive than a light person. We know that it's harder to push a big cart than a small cart. And we just say, oh, those things are obviously the same because we've lived it with that our whole lives. But there's no intrinsic reason why they should be the same. It's not obvious that those things would be the same force, but they are. So there are a lot of theories trying to link them, saying, here's why the same thing that causes this acceleration is the same thing that also causes like gravity, or impacts the forces of gravity. So But there's no theory. It's like, are these actually two different things that have the same underlying cause? Are these two different things that happen to be the same? There's like some underlying reason that causes both of them? A lot of theories to propose about why they're connected, but I don't know why they're connected. Okay? That's the concept of mass. Now let's move into the law of conservation of energy. So, okay, this whole time I've been lying to you because I've been talking about E equals mc² as saying, here's how you can convert mass into energy, and here's how you can convert energy into mass. But that's kind of not the best way of thinking about it, because what Einstein realized is that mass is just a kind of energy. This is like a definitional issue. It's like definitionally true that mass is a kind of energy. We're just defining it as a kind of energy. How we define things in physics is a difficult problem. Basically, like if you have a category, in this case, the category is energy. Whether something is in that category depends on whether its properties are like aligned enough with that category that it makes sense to lump it in with the same category as opposed to saying that it's something else. But physicists determined that the most valuable way to talk about mass is to say, actually, it is a kind of energy. And this is true, like you have to internalize this, right? There are many different kinds of energy. There is gravitational energy. Wait, is that true? Sorry, no, there's not. There's kinetic energy. There's gravitational potential energy. That's what I was thinking of. There's like electric energy. There's many different kinds of energy. Like, let's look it up. There's thermal energy, nuclear energy, radiant energy, sound energy, mechanical energy, chemical energy, thermal energy. Okay, there are many different kinds of energy. This is obvious. The insight of Einstein is just to say, mass, that's one of those. Mass is just one of these kinds of energy. That's what it is. So to say to convert mass into energy doesn't actually make a lot of sense, because if mass is already a kind of energy, then what you're really doing is converting one kind of energy into another kind of energy. In this case, you're converting the mass kind energy, the mass type energy, into other type energy. Like you're converting mass kind energy into thermal kind energy or something. And that's an operation you can do. Different types of energy are converted into other kinds of energy all the time. And E equals mc² also tells you when you convert this kind of energy into another kind of energy, how much mass are you going to get, right? So we have the law of conservation of energy, and the law of conservation of energy is always true because everything was always energy in the first place. You're not really converting it to mass, you're converting it to one kind of energy, okay? Makes sense. That means that this equation, what is this equation actually doing? Okay, well, we have this symbol called E, which represents just energy in general. We're not describing what kind of energy it is, we're just saying energy in general, okay? That's E, the symbol E. That makes sense. C, we already understand. C is just the speed of light. 2 is just 2, so we're multiplying it by itself one time. That's squared. What is the M? The M is just a unit which describes a particular kind of energy, and it also has a particular unit of measure for that. So, for example, if you convert meters into kilometers, occasionally you might want to do that. You have to multiply it by 1,000, not too hard, but that's a unit conversion. Similarly, let's say you need to convert miles into meters, okay? If you want to convert miles into meters, then there's an equation that you use that tells you how to do that conversion. You say, I have a mile, I want to see how many meters I can get. That's 5,280, whatever. That's the unit conversion. But I don't like that analogy enough, because that's still just measuring the exact same thing. What if you're measuring something more specific and want to convert it into something more generic? So an analogy for that could be you want to convert nautical miles into miles. So a nautical mile is a unit of measure on the water. Okay, that's just like something that I don't know. Fishermen are special. They need their own special unit of measurement. So they invented nautical miles to say there's 10 nautical miles until the next buoy. It's a unit of measurement on the water. And then you have regular miles, which are just a unit of measurement in general, and are not the same. So if you convert nautical miles into miles, then you're converting something specific into something more general. But you also are like having to multiply by a number to do the unit conversion because they're not the same unit. So the way I think about E equals mc squared now is to say, like we're doing a unit conversion between m, which is a specific kind of energy, and it is also using different numbers in the same way nautical miles and miles are using different amounts. Well, m is like a measurement of an amount of something. And so if we want to convert that to say, oh, for this m, how much energy do you have? You have to do the unit conversion by multiplying it by, the speed of light squared. You have to multiply it by this number in the same way that if I was converting from, miles to meters, I would have to multiply it by a number to see how much I get. Also, that equation holds true in the case where you're actually doing a conversion. So if you just want to say how much energy do I have in this mass, then it tells you. But if you're also doing a conversion from mass into some other kind of energy, then it tells you how much of that other kind of energy that you're going to get. Because of the equivalence of energy, energy can't be created or destroyed. If you're creating a different kind of energy, it needs to come from somewhere. And if it's coming from mass, then however much mass you destroy, then that's how much of the other kind of energy you're creating. So because of that equivalence, it does hold for conversions that E equals mc squared tells you how much of the other thing you're going to get. But that's not true because you're doing an action that's converting. There's no arrow. The equal sign is actually the correct sign here because you already had that amount of energy and you're just doing a conversion after the fact. You can do that, but it was already there. I don't know if that makes sense. Yeah. But that's why we use an equal sign instead of some other word like billets or arrow or whatever. It's because you're saying, oh, here's how much it equals already. It was described to me where mass is stored energy. Different kinds of energy can do different things. If I hold up a ball really high and say, I'm going to drop this ball, haha. When I hold up the ball, that ball has gravitational potential energy. So that energy is stored movement. It's stored action. The ball is still, but the ball can fall. So it's saying how much potential there is, right? It's sort of the same deal with mass, where mass is stored energy. It is energy, but it's how much energy is doing the action of being responsible for keeping this thing in the state of a particular atomic configuration. If I had to describe the whole thing together, I would say and mass is the kind of energy that says that it's related to the configuration of subatomic particles into atoms and keeping hold a particular state where those subatomic particles are in a particular configuration where it leads to that atomic number or atomic weight, where it says it's this amount heavy. And when you have that atomic weight and you can add that across all of the atoms that you have, then it's what that's responsible for is saying how much this object can accelerate other objects, but how much it impacts the momentum, and also how much these objects are gravitationally attracted to each other. So that's it all coming together. Although I may have phrased that sentence a bit weirdly, but that's the concept of mass, sort of, and that's what E equals mc² means.